This is another TCP Analysis talk. It's about more complicated things. So if you just learned how TCP works, this may be a bit confusing. The funny thing here is that I put this together without really looking that much at the traces myself. I saw them a couple of months, years, or whatever ago. So if I'm confusing myself during this talk, that is for you to see me trying to find my way through the traces. I did that on purpose. So it can happen that I get lost in my own traces. It's quite possible. So I try to get a little bit of that packet doctor thing on my own talk as well. Who has seen the packet doctors yesterday? Okay, so the rest will see a single packet doctor struggling with traces. The idea here was that very often everybody's talking about very simple things when you're doing analysis, like, hey, I see a retransmission and there's some time that is gone by, so this must be a problem and problem solved or topic solved. But sometimes it gets more complicated than that. And I turned in this talk just to show a couple of things where we were looking at traces that weren't that really easy to solve. It all comes down in the end to the amount of experience that you have. There's one trace in here where people may spend hours and days on and not really seeing what's happening. And if you got enough experience, you will look at it and say, well, this is this, like half an hour done. And experience, unfortunately, is something that I can't just hand to you. You need to make it yourself. As I always say, experience is needed most right after you needed it. So that painful times when you find out that something works in a certain way after spending hours on it, that's the most valuable time, because then you're like, hey, now I know how this goes. And that is the same for network analysis, basically. So I can show you a couple of things, and my plan is to give you some ideas of things that I've seen, and maybe when you see something similar, you remember like, there was this talk and there was something about this, and then you're a little bit faster. It's not going to help you like solving complex problems in half an hour. That's not going to happen probably. But if you get a little idea that is quite similar to the challenge of Sake yesterday, if you know what you're looking for, or if you have a couple of ideas what to do next, that is always helpful. Because if you don't, then you're like, now what? Stuck. And we don't want to have that, right? Okay, so about myself, I'm working still for Airbus. That hasn't changed since the first talks that I gave here. I'm active in the Wireshark community in a way that I write a blog post or blog posts. If you haven't read it, maybe you may want to. I will reference to some of the blog postings probably during this talk, because my idea of writing blog posts is not to have one blog post every couple of days to show you that I'm very active writing something, but I'm writing blog posts sort of like a collection of knowledge and collection of tutorials that you can look up even years later. So sometimes people are pointing to my blog post from 2013, which is about 4 years ago, and they're still kind of valid or mostly valid, and if they're not valid anymore, I will update them. So it's like a resource, sort of like an online mini book, so to speak. Twitter, if you want to do the Twitter thing, I'm PacketJ. I'm quite active on the Wireshark Q&A page. Depending on the questions that arise, if somebody's asking something about Wireshark code stuff, I'm like, I'm out, because I have no idea. And SharkFest, obviously. Also, I made Trace Wrangler, if you haven't heard it by now. Trying to get more than 5 people interested in that. Sometimes it works, sometimes it doesn't. Take a look if you want. So, the main challenge that I have with packet captures coming to me, or that I have to analyze, is always the capture quality. I've had captures where somebody said, hey, no problem, we will do a capture at 7 capture points simultaneously and send you all the files, and then you can find the problem. I did 2 of the 7 myself, The quality was acceptable, good enough, depending on what I could do at the point. I had to use a span port, so that's not the optimum that you can do. Tap is always better. But then I got the remote captures from somebody else who did them for me, and they were completely useless. Like spending a day capturing stuff, then getting results back from somebody else who's captured something on I don't know what, and you couldn't use them at all. So in that way, doing an analysis, if the capture quality is not good enough, you can forget it, basically. There's not so much that you can do then, depending on what the problem is. So capture locations, we have 3 of them, at the client, at the server, and somewhere in the middle. And please note, I'm saying at the client, at the server, and not on the client or on the server, because I don't like those. Why not? Anybody knows why it's not a good idea to capture on the client or on the server? Yeah, we have a lot of things going on where the trace will lie to us. So one thing everybody says is packets never lie, and I'm like, no. They do. Sometimes, depending on what you captured, how you captured. But I mean, if you do a perfect capture with a tap, full duplex, with a great capture device, yes, packets don't lie. If you did it locally on a system that is doing so many things at the same time, being overloaded and stuff like this, packets do lie. And the problem is that you need to know in which way they are lying. So if you see a huge packet, 16K or something, and you know, well, that's not in the specs anywhere, well, then you need to know it's just a lie. It's a packet that hasn't been cut into smaller packets, and then the troubleshooting gets a bit more complex. Or maybe impossible. Can happen. So please try to get a good capture quality, otherwise all of those will probably be much harder to do. All right? So I did a couple of slides here to show you what the difference is between the capture location. If I'm capturing at the client and packets are going back and forth, you can see that the client sees a long time between, or relatively long time between his request going out and the answer coming back. So the capture device sees almost the same thing, maybe a bit quicker because it's a little bit in front of it. If you move the capture device to the server, the picture is quite different because you see that the time between the request coming in and the answer coming out may be a lot faster. So it's quite important to know where you are, because if you're talking about timings and what it took and what happened, you need to know where you were when you captured. If you're at the client, the picture is different than from the server. If you're in the middle, then it gets even more complicated because you will see, like, let me check if I can get this thing to work. You can see here that this time, at this location, the capture device realizes for the first time that there is a packet. But the whole travel distance here, from here to there, it doesn't know. It sees the packet at that point in time, and that's the first it ever sees it. Same with the answer. The answer is first seen here. So for the capture device, this is the time it took. And the travel time to this and that end, it doesn't know. Okay, so you need to be aware where your capture was. So one of the effects that I'm trying to show here is, and I think this is an animated slide I made just maybe 20 minutes ago. It looks like this. If the packets are going out from the client to the server, you will see that basically the client is sending a lot of things. The capture device will see many packets from the client before the first packet from the server arrives. So that picture is different than if I move this a little bit to the right, because then you will see 2 packets from the client and the packet from the server coming back. Well, in this case, the green arrows should be a little bit lower. But you can see in the capture the order of packets will be quite different. Yeah, so that is really important. Never look at the order of packets in a trace file, because they depend on where the capture was taken. It's more here or more there or in the middle. It's completely different things. So what can we do to really find out the order of packets that were sent and acknowledged? Yeah, look at the handshake. That is a valuable idea to do that. Why? because we need to know what the round-trip time is, okay? But for packet ordering, what is the one and only thing to look at? Starts with an S and ends with sequence. So we're looking at packet sequences, sequence numbers. They tell us which order of packets should have happened. Sometimes they may trick us, which is the problematic part in TCP, because you may see a retransmission which has an older sequence number appearing later than it should have been. And if you don't have the original, your ordering gets quite out of order, and that, in that regard, your idea about looking at the handshake is quite important. Because the handshake will tell you how much time does it take from one to the other and back. And if something arrives much later, it's probably a retransmission. Okay, so timing is the one key thing that you need to look at. And we have many questions on ask.wireshark.org where people are confused by seeing packet sequences in a certain order, not thinking about what the time is. Where were they captured? How long did it take to travel? Is that the real order that they arrived at the one point or the other? That is important to know. So, some guidelines. Watch out for initial round-trip time, IRTT. So everybody knows what that is, initial round-trip time? Who doesn't? So you all do, great. All right. So I don't need to explain it, right? If you need a hint about this, go to my blog and there's a post called Determine Initial Round-Trip Time. Google for it, you will find it, and it will paint you some funny lines of why this is the way to do it. Basically what we do is we look for the SYN, the SYNAC, and the ACK. And the time from SYN to ACK is your initial round-trip time. So if anybody of you is now like, wait a minute, it's not from the SYN to the ACK, it's from the SYN to the SYNAC, read the blog post. Because it is, okay? From SYN to ACK, handshake, full time. The next thing that many beginners don't do is they don't isolate TCP connection, and it's quite funny to see them try to match sequence numbers from different TCP connections. It's like, why doesn't this? Especially if you do relative sequence numbers. Relative sequence numbers are only allowed if you know what you're doing. And if you get into trouble because of relative sequence numbers, turn them off. Yeah. I know that many people don't like the long real sequence numbers because they're so long, but here's a little trick for you. You don't need to remember all of them. Just remember the last 5 digits. Why is that enough? I always do that. I only look at the last 5 digits of a sequence number because the biggest packet that you can see has how many bytes? 1,000 something. Yeah, or if it's a jumbo frame, it's 9,000 whatever. 4 numbers, 4 digits. So if you add a 4-digit number to any other number, the only thing that can change are 5 digits with an overflow to the next higher number. So the only thing that can change are the last 5 digits. If you see a sequence number where more than the last 5 digits change, you know that you have a gap. Or your capture quality is not good enough because you have huge packets maybe. Yeah, so sometimes that is a problem that you need to work around, but very often if you're using absolute sequence numbers, just look at the last 5 digits. That's what I do. Isolating the TCP connections in 2 different ways. Either use the 5-tuple. 5-tuple means IP A, port A, IP B, port B, and of course being TCP. With that, you get a filter that basically says IP address equals something and port equals something and IP address equals something and port equals something, and then you have your connection. And then there's the stream index, which most people use by saying follow TCP stream, which I absolutely hate because it's an extra step to close this content window again, and I don't like clicking one extra click. It's too slow for me. And some of the core developers look at me like, what are you doing? It's too slow. Really? Yeah, I even hate the find dialog because the mouse distance is too long. Yeah, the find button is all the way on the right and I don't like it. Yeah, and everybody's like, what's he talking about? Yeah, I'm really fast when I'm in the zone, like a programmer being in the zone, looking at packets. I don't want to move more than I need to. I would do everything with keyboard shortcuts if I could, which I can't, but I would. All right, if you know the capture location, great. If you don't know it, find out from the packet capture. Who knows how to do that? How do you find out where the packet capture was taken? You look at the SYNAC. Yeah. You look at the three-way handshake, and you can find out where it was taken by seeing where the small numbers are. Yeah. Usually the numbers are really small for the one and very high compared to that for the other, and then you know, oh, it was taken here, it was taken there, it was taken in the middle. Timing is everything. So if you're doing advanced TCP analysis, you're looking at sequence numbers and delta times, sometimes relative times, but those two things, time and sequence numbers. That's what you do all day. And that's where we lose usually all the beginners, because it's hard to concentrate on that if you're not really used to it, and you need to practice, 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 practice. I've done this for 13 years now, I think, or 14, so I've got a lot of practice. So I can sometimes even jump over big amounts of packets because I can see out of the corner of my eye that the sequence numbers are nice and good. So I try to find the locations where it's not good. So the one thing that you need to have if you're doing advanced TCP analysis is, and that is the one thing Hansang always says, he won't talk to you if you don't have a delta time column. Yeah, if you don't have it, you're not serious about packet analysis. And yeah, it's kind of like that way. So you need to have a delta time column. I hope everybody has one, because it's really, really, really important. Okay. Enough slides. Let's just try to look at some packet captures. Hello. Picture, please. Come on. Okay. Okay, my first trace, it's called Citrix. Who knows Citrix? Or Citrix, or whatever you want to call it. Who's afraid of it? Huh? Again? You've heard it? You heard about Citrix? Of course. Who thinks it's a scary protocol? Why is it a scary protocol? It's asynchronous. Usually what we're used to is that a client says, hello, dear server, I want to talk to you. And the server says, great, let's talk. Okay, let's talk. That is the handshake. And then the client says, I need this from you. And the server says, there you go. And as an analyst, we're like, where's the question or the query or the request? Where's the answer? How long did it take? Is it good enough? Great. If it's not good enough, bad. We found something. With Citrix, it's similar sometimes, but not always, because it's asynchronous. Citrix is a remote desktop protocol. So think of this. The client connects to the server. The server says, hey, you want to see a screen? Okay, here's the screen. So far, so good. But then something on the screen happens. And the server's like, hey, you didn't ask for it, but here's something else, because you need to paint this, please. So the server can send something to the client without being queried at any point in time. So if you're looking for large delta times, that's not going to work most of the time. Yeah? Very often we're looking for where does it take a long time. But if the client just sits there for quite a while, and then at some point the server sends something because something happened on the desktop, you will see a packet coming from the server, and you're like, oh, this took forever. And then it's like, yeah, but he had every right to do that, so this is bad. So Citrix analysis is always a big challenge. This is a real simple one. I'm just starting with this topic just to let you know that Citrix analysis is always something where I get really, really careful, because you cannot guarantee any kind of time to resolution value, because it may not be that simple. Just to let you know, the most complex Citrix analysis I ever did was for a company that is doing 3D drawings for satellites with Citrix. So the designers sit in one town, and the servers they're working with are 500 kilometers to north. And they're rendering everything that they're doing. And satellite drawings are not your typical something that you can print in a 3D printer. They're insanely complex things. And the problem they had was if they turn the model with a mouse, sometimes they click on something because they think the turning is complete, and then it goes one step further and they click on something completely different. And they have to... totally annoying. It costs so much time. The problem with that is that all the 3D drawings are rendered on the servers and then set as a movie to the client. And we troubleshot that one, and that was the one where they told me, hey, we can get you packet capture from all the way, but their quality was like unusable. There weren't even Citrix packets in the traces that I got back, and I'm like, what am I supposed to do here? So that's the one I couldn't solve because they canceled the problem thing and went back to non-Citrix drawings, I think. So Citrix is a problem. You can see that it's light blue because I colorize Citrix just so I know where my enemy is. Citrix protocol is something that I need to be aware of if it happens in the trace. This was actually a relatively simple thing, but I wanted to use it just to show you how you can look at the timings here. Where's my... there. Okay, so you can see it's three-way handshake. And one trick that I already showed, if you're trying to look at a couple of packets and not getting confused with anything else, just remove everything else. All right, so what I do very often, for example, is frame.number less than 4. Now I only have my handshake here, and I can concentrate on that. Of course, I don't do that anymore with the handshake, but sometimes with other things. So frame range filter is quite nice to just remove everything else that may distract you. So what we can see here is we have a delta time from the SYN to the SYNAC of 714 microseconds. Is that fast? Oh yeah. But the ACK is 890, I think. Let's zoom in. So where's the capture location? At the client or at the server? Server? Trick question. It's so fast, it's hard to tell. But it's more likely that it's close to the server, just because it's a little higher. But with microseconds, I would not go and say, I'm pretty sure it's right there. It's like, probably, it may, but maybe it's in the middle, I don't know. Yeah, sometimes you have timings like this where you're not really sure where it is. Actually, this was captured at the client. So, yeah. If you have timing that fast, you need to consider that the nodes also need to do something in their TCP stack. It's not like that they're instantaneous. Yeah, the timing is too fast for you to really tell where it is. So in this case, I know it is at a client because I captured it at the client. Yeah. If you've ever done troubleshooting with a really huge problem, I can recommend doing the capture yourself right next to the person having the problem, because then you know what is going on. That is sometimes invaluable by reading the packets, because you know that, oh, we did this and we did that, and you wrote it down. Writing things down is the most important advice I can give you. Because if you're doing the analysis 1 week later or 3 weeks later, you're like, this trace, what was it again? And that happened to me. And then you're in big trouble because you're starting to sweat like, I need to find something, but I have no idea anymore what I was doing. Yeah? The MAC addresses on different subnets. Yeah. Yeah, if you look at the MAC addresses, sometimes you can tell that there's a router in between, so let's check. I think they're anonymized, so you don't know. Yeah, it's Trace Wrangler. If you see a MAC address starting with F2, that is Trace Wrangler. Because I'm setting the locally administered bit so that you know this is not a real MAC address. So if you see F2 as a MAC address, usually it's Trace Wrangler. And the other thing to find out if it has been anonymized is quite simply go to statistics, capture file properties, and it will tell you it was sanitized by Trace Wrangler. Yeah, and that's the first thing I usually check when somebody sends me a trace. Did they sanitize it? Just by looking at this. Well, if the file name is _anon, I know it has been tracefinger because that is the standard file extension that it gives it. All right, so looking at the handshake, we don't know where it was, but I know where it was, so let's take a look at this. The problem was that the user complained of Citrix suddenly completely freezing his screen, not being able to do anything anymore, and not being able to work. It was in a bank. They should be able to work. He wasn't. And the interesting thing was that I was sitting next to him when his screen froze. And it froze for about, I don't know, like 60 seconds. 60 seconds is like eternity forever in a network. So just to start things lightly, let's see if we can find the 60 seconds somewhere. So no scrolling, as Laura said. Ignore that, I'm scrolling. And if you're experienced, you will be doing this a lot, like, I don't care, I keep going, I don't care. Stuff like this. Oh, that was red stuff. Oh, red stuff. Window full, zero window. Window full, zero window. Is that bad? That's pretty bad. It depends. Okay. Yeah, I'm leaning to be the zero window phenomenon being one of the things where the it depends for not being bad is pretty small. Zero window is very often bad. Like 90% or 95% of the time, a zero window is bad. Sometimes there's a special case like I presented in my first talk where there was this old printer that had to get the gears going and everything. It was sending a zero window to stop the print job from arriving because it had no cache at the time, or there was no cache in that printer. So it used the zero window to stop the transmission before it was ready to basically print the stuff. That was one of the situations where the zero window is kind of bad because it means this device is so old that it's slowing things down. So zero windows is very often a bad problem. Okay, let's check out what's going on with this. I have one thing that I often do here when I have no idea what's going on, and that is tcp.analysis.flags, just to get some idea what is going on. Window update, is that bad? No. Who thinks it's not bad? Window update usually is not bad. It's just saying telling you, hey, I got more room now. And that's good. It's a recovery process, right. All right, so let's see. What do we have here? Windows, zero update, zero window, more zero windows. It's not looking good, right? But it seems to recover at some point. Then it got more problems here. More problems. Okay. Let's see. Let's go down further. Oh. What's that? What's happening here? I can make it bigger for you because I think it's really small on the screen. We're missing some packets, yes. But the one thing where I always really get into found something is when you see the zero window probe and the zero window probe ACK. Because a zero window can happen, and if it happens, what do you do then? What do you do if you see a zero window? Are you going to write a report like, hey, there's a zero window and I solved your problem? Wait for? Yeah, a window update, but the window update is only half of the thing that you're looking for. What are you looking for based on the zero window and the window update? What is the interesting thing here? The time. How long did it take? Because I've seen zero windows where the window update arrived like 5 microseconds later. So it was zero window and then there was a window update telling me, hey, 16K. So it's always the question of how much time did it take? So how much was the transmission slowed down by the zero window process? And if it's really small and not really having an impact on the throughput that you're seeing, write it down as, hey, I saw this, I think the hardware is on the edge of being, maybe you should get something faster. But if it's not costing you much time, you will have a hard time telling anybody like, hey, this system is like, you need to replace it, because it's not happening. But if you see a zero window probe, when does that happen? The application on the receiving end doesn't read the buffer, so it's quiet and doing nothing. And then the sender gets nervous at some point and says, hey, I still got more stuff for you. Are you going to send me a window update at some point, please, maybe? And if it takes ages and ages, like hundreds of milliseconds, which is ages in a network, at some point the sender will be like, poke, poke, poke. Tell me something, what's going on? And that's the window probe. And then you get either a window probe ACK back telling you, hey, I'm still at 0, or you get a window update. A window update would be a resolution, so it would work again. But if you get a window probe ACK, that means, yep, still busy, don't talk to me, don't have time for you, I'm slow. Okay, and we see that here. So we have quite a few window probe, probe ACK, probe app. So let's do a conversation filter. I think it's only one conversation in this trace, but I want to see everything now. So we see there's stuff working, and then suddenly it says window full, 0 window. Window full means the sender has sent as many bytes as the receiver said it could handle. Now there's a 0 window.
So in this case, the server is?
The server is sending the probes. The client is the one that is overloaded.
Okay, so we got window full on third row down.
We got,
And the source
yeah.
is the...
Window full is coming, the window full is something that Wireshark tells us for the data arriving from the server to the client.
Oh, okay.
The server is the 10.10.10. Whatever. It's the Hansang scheme. His clients are always 192.168 something, and the servers are 10. something, and I adopted that because we're presenting a lot together, and I don't want to confuse people. Because if I would I could do a funny thing, naming my servers 192.168 something, and everyone was like, what is going on? So 192.168 is usually the client in those anonymized traces. So what's happening here is this server is sending stuff. At some point, Wireshark says TCP window full. By the way, we have many questions on us where people are, hey, why does the server send a window full message? It doesn't. If you see square brackets, it's a Wireshark notification kind of thing. So the server gets a bit annoyed and says, 0 window probe, what's going on? And you can see that there will be 0 window probe X with TCP 0 window, so the client keeps saying bad, 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 bad. So back to the problem of timing, what do we do now? What we do is we check for, let's say, the time where the window full is given. You can see you have a relative time here in the front. And the question is, when does the window update arrive? 18 seconds. Yeah, that's not good, right? I mean, waiting 18 seconds for something to unfreeze will be something where the user is like grabbing the phone, hello IT, did you turn it on and off again? Yeah. So, yeah.
Does window full literally mean, 0 window literally means 0, or does it mean less than MSS? Anything like
0 window means my buffer as a receiver is completely filled to the last byte of data.
The notification from Wireshark.
Yeah.
Does it mean literally R1 equals 0, or is it R1 less than, like there's frozen and then there's nearly frozen?
Window full message at Wireshark is calculated by looking at the bytes in flight. But, yeah? 0 window. 0 window is when there's a 0 in the window size value in the TCP header.
Okay, so there's another condition when it's less than MSS.
If it's less than MSS, that was called by Sniffer the silly window. And you still can send, but not a full segment. If you see something like this, I don't think that there is a expert symptom for that in Wireshark. Is now? There's not, right. Silly window basically means it's highly inefficient. That is something you need to find out as an analyst yourself. What I've done, I think, in my color profiles is I set a color filter that tells me, hey, here's a window size less than MSS. And I assume MSS to be 1460 for practicality reasons, because a dynamic thing determined from the handshake, I don't need that kind of thing. But if a window drops to 1 segment or less than 1 segment, it's always like, uh-oh. Yeah. All right, so 18 seconds. This is a problem, but it's not the 60 seconds that I timed. Basically, I sat at the client with a stopwatch when that happened, and I know it's longer than that. So let's see if we can find something else. There's more zero window probe ACK, window update stuff. I could sort now by delta time and find it real quick. You were? Didn't listen to you. I should listen to Betty.
Like a mind melt.
Yeah.
Open mind melt.
Let's sort by delta time again, so I get the high numbers up there. Okay. That is port number used after 202 seconds. Can we ignore that? Is it important? Who wants to ignore a port number used after 202 seconds? Why? Because the timeout is 2 minutes, which is 120 seconds. Doing something after 120 seconds, like a port we use, we don't care. All right? So, doesn't matter. All right, zero window probe at 28 seconds. That sounds really nice, because that means somewhere there is a window probe being sent after a long time, so there must be a zero window condition somewhere that we don't see right now. But what we can do now is just click on the packet so that the focus is on the packet, and then just sort by number. And now I'm here in the middle of the problem. And if I do the same stuff that I did before, setting a time reference, you will see that I have a window update time of exactly 60 seconds. From problem to it works again, 60 seconds, and that matches quite closely the timing that I had on my stopwatch. So I put in my report, there's a problem. What else did I put in my report? Who's causing the problem? The client. What is my proposal, or what did I propose to solve the situation? Because if you turn in a network analysis report where you say, hey, we saw a problem, it looked like this, thank you, here's the invoice, they will be like, what are we supposed to do? So what is your recommendation? What should they do? Add memory to the client. Maybe it's a memory bottleneck. What else? CPU maybe not good enough. Disk space. Basically, we're talking about a hardware bottleneck. Somewhere on the client, it could be CPU, it could be memory, it could be disk I/O, it could be anything. Here it was a thin client called Eagle. Not the bird, but the German word eagle means hedgehog. And that's the company that built those. And what the user was doing at the time, and that was a funny thing, because usually users don't do that if you're doing a network capture. He was watching a YouTube video on this. And if you want to kill Citrix performance, watch a video. Yeah? Because so many updates need to come in, and it needs to paint stuff, and it's really stressing it out. I think Citrix is mostly done for word processing, where you type one character and another character and another character with little updates on the screen. But if you're watching videos, and a lot of people do this apparently on a thin client, mostly because they don't get desktops anymore or laptops, well, this can happen. And then if you don't want to prevent them from doing that, if you're allowing private use of the company resources, which most German companies, for example, do, then you probably need to upgrade your hardware. And I told them, this thin client is not fast enough to do whatever the user is doing. It's not my problem if he's doing something he shouldn't be doing. I'm only saying, upgrade the hardware. Find out what the bottleneck is, and that is something that I'm, as a network analyst, am not responsible for. Find out what the bottleneck is, do something. but it's a hardware problem. And I can see it on a network. It's not a network problem. Very big red letters, not a network problem. Okay? You see the zero window, the probe, everything visible on the network, but it's not a network problem. They came in and hired me to tell them that the users having real problems and that they are real and that they're caused by the users. I omitted in my report. I just told them for whatever he's doing or she's doing, the device is not fast enough. And if the company then wants to ask the user, like, what were you doing? You were supposed to do SAP. And he's like, oh, I watched the tutorial video how to use SAP. Oh, that was, yeah, probably. I was troubleshooting one company in the US once where they had, I think, 300 employees from Vietnam because they were not that expensive, but they keep watching their home TV over the internet link, and that was a T1. And that didn't work. So, funny things. You had retransmissions like crazy because the pipe was completely full all the time, and you had outgoing retransmissions. You saw retransmission leaving the company like crazy because clogged pipe. So it happens. Video is the killer of everything if you're not careful. All right, so if somebody wants to, I think I wrote in the session description that I will put the traces somewhere, and I totally forgot to do that, so apologies. I will put them somewhere afterwards, probably at the location mentioned in the thing so that you can find it, and I will name it accordingly so that they can get them, okay? Sorry, it was just, I mean, everybody, after SharkFest US, if you ask anybody, they will tell you, I don't know what happened, but somebody dropped 16 tons on me, like the Monty Python sketch. We were all completely overloaded with whatever, so there was almost no preparation time for anything, especially not this kind of thing. And then Hansang couldn't come, and I had to take over his slot, so my bad, basically. Okay, next one. DUPAC fun. What's a DUPAC? I mean, this is an expert talk, so or advanced talk. You should know what a DUPAC means. What does it mean? Who's trying the it depends thing? Because it depends. Maybe packet loss. Very good. He avoided the it depends thing by saying it may be packet loss. Yeah, it's one of the it depends things. Okay? Yeah, the receiver is basically saying, I got something, but it's not what I wanted. So when does that happen the most? When there's packet loss. Because you're sending packets, and there's a gap, and then the receiver says, wait a minute, I expected something else. DUPAC. Send me something starting here, not there. Okay? What's the other thing of it depends? What else can it be if you see DUPACs in a trace file? And that's my favorite thing because it happens like in 50% of the times now. What? Out of order packets? Yeah, maybe, but that's not the main problem. I had one colleague a couple of weeks ago in those crazy times when was doing 5 jobs at the same time, and he said, well, we were having trouble with a WebEx application, and he said, I got a packet capture, and it has 33% of DUPACs. 33%. And I'm like, no, you don't. Yeah, I do. Here's my trace file. And I said, okay, let me take a look at it. So what happened? 33% of DUPACs. What does that mean? Duplicate packets. Yeah, people are capturing, and coming back to capture quality, it's a big issue because people with, in Germany we call this gesundes Halbwissen, healthy half knowledge. They're like, oh, this thing is black and red in Wireshark. I got a problem. Oh, let me see how many problems I have. 33% of problems. Oh, we have a problem. And I was like, okay, can I have the trace file? So I got the trace file. I ran edit-cut -d or -d for a deduplication. Ran the file through it, gave it back to him like, you don't have a problem. He was like looking at it like, well, what did you do? This looks fine. I'm like, yeah, it looks fine. You just captured in a way that you shouldn't have. Or you can capture in that way if you know what you're doing and deduplicate it before telling me it's a big problem here. Because if you do that, in the end, the analysis report must be able to be handed out to Sake, Christian, Hansang, and he must come to the same conclusion than I do. If not, I'm in trouble. I've done that. I've handed in reports where I wasn't sure if I was completely right, and if you have somebody on the other end of the report receiving it who's checking what you're doing and he's maybe better than you or has at least the same level, you should be sure about what you're saying. So reports are very important in a way that they need to be precise and correct. You may make an error in there, which is what I told you at the SharkBites. It's quite, I mean, my first report I ever turned in was totally correct, but getting there with a totally incorrect way. So I said, this is the problem, and it was that problem, but my way of finding it was completely bogus. It was sheer luck that it was that same thing, so it can happen. But we need to try to be precise here. So let's look at this thing. DoopX, that's what the trace is called, so let's try to find some DoopX, because otherwise my time is running away. TCP.analysis. It's too small. Let me zoom in. Okay, so this will take a while. Okay, do we have DoopX? Yes, we do. How many of them? I mean, if you want to have a quick look, 4,192 out of almost 1 million packets. So is that bad? Is that a bad ratio? And once again, it's time for the two famous words that begin with "it depends." Because, yeah, maybe, maybe not. If you have duplicate X every couple of packets, but that it's not costing you any kind of time, or it's only just an out-of-order arrival, we don't care. It depends on how closely they are together. So looking at those, you can see in the Zoom screen up there already, how high do they get? The highest number you can see right now is 62, right? What does that mean, 62? DoopX number 62? Again? I've seen the same acknowledgement for the same packet 62 times. So how many packets did arrive for me to send you 62 times DoopX? It depends on how many ACKs you send per packet or how many packets you ACK in one single go. So usually do 1 per 2 packets. So it's at least twice that. Yeah.
Aren't you going to add every other packet once
Yeah.
you lose a packet? Is first thing you can add, so we'll add
Yeah.
every packet?
The ACK frequency changes with packet loss. It depends on the stack, how it's implemented. So it's quite possible that there are ACKs every packet after packet loss. Yeah, it's quite possible. You need to know which stack you're looking at. But for simplicity, I always say it's every other packet. If you see, and if you are looking at something where you think it's every packet, you need to go and look at the sequence and ACK numbers and check what is happening. And that is the things that take most of the time when we're doing that. Right now,
If you were using stack, you would do every packet. That's
yeah, if you have stack, you have a good indicator that tells you what is going on. So let's check. Is 62 the highest number that I have here? I don't know. 90, 100, 200, 300, 400. The highest number is 1,111 duplicate X. And everybody should be now like, uh-oh. That is a lot. It's the second highest number I've seen. And the highest number is also in this trace. It goes up to 1,129. So this happens at least 2 times. What is happening here? What is the round trip time? Very good. So if you have no idea what's going on, first thing is get your bearings, find out what's happening here, and you need to have the round trip time for that. That is the literally first thing that you need. There's two ways of finding that one out. The first way is to look at the handshake. The second way is using a recent Wireshark version where the core developers finally listened to me and put something in Wireshark that will let you know what the round trip time is. And let's try that. I hope it works. Go into this TCP layer and look at the IRTT field that is in there. That is really useful because, like Betty, I don't want to scroll all the way up when I'm somewhere where it's interesting just to find out what the round trip time is because I forgot to do that at the beginning of the trace. Now the field is in there. And this field it should be a little bit golden because it's kind of magic. You can do some cool advanced filter tricks with it. For example, try filtering on or extracting all 3 handshake packets. That is a challenge that wasn't possible before we had IRTT and the window scaling thing, because the IRTT field will only be there if you have a full handshake. So if you don't have it, if you don't have a full handshake, there will be no IRTT field. So that is a good indicator of is there a complete handshake, and then try to get it. I wrote a blog post about how to do that, so if you want to do it, read it. So our initial round trip time is 22 milliseconds. Good, bad, something? Not outrageous. Well, let's say this communication started in a city in Germany and ended, or the other side of the thing was in a city 400 kilometers south. So 22 milliseconds, quite good. I don't think you could get any better. And the problem description of the customer was, well, we got a connection that starts with a 10 gig line and it ends at an LTE thing that has 150 megabits. The throughput we're seeing is 12 megabits. So it's less than a tenth of what we're expecting. What is going on? Too large? Who was? Too large window size. How big is the window size? 4 megabyte, is that a big window size? And again, it depends, right? But where did you find the window size? Calculated? Okay. I mean, a 4 megabyte window size is something that you can encounter quite often, depending on how big the pipe is, what the distance is, the famous bandwidth delay product. But let's, in this case, go to the handshake and see what the handshake is doing. For that, I need to clear my filter again, which takes forever. So here they start with a window size of 8K, scaling of 4. So this one has a calculated window size here before it happens. Where is it? Okay, I need to go to the right connection because this is the one that starts. We will see that the window size 46, calculate 5888. So it starts low. But this one, for the receiver, I think that's the receiver. Let's see, who's who. This is the client. The client gets the data, I think. Yeah. So the client is saying in its, I don't know, if we're starting from here, packet 1, 2, 3, 4, 5, 6, 7, 8. In its 8th packet, it's already saying window size 4 megabytes. Now, is that common or is that kind of like,
Static value.
It's a static value. Normally what happens with the window size, it's increased over time when the receiver feels like this is working, the throughput is fine, no packet loss, increase the window size, increase it, it grows. This one here is static, 4 megabytes all the time. And if you see something like this, like a static window size being that big at the beginning of the communication, somebody's not doing something right. So either the stack on that thing is kind of weird, but I know it's a Windows system, so the stack should be fine. But something is putting a huge window size into the packets, 4 megabytes. That is quite big. And it doesn't change. It keeps it at 4 megabytes. So no, there's nothing in between, just switches and a long-distance line. Maybe a router, but nothing that is firewalling, load balancing, nothing of that, things that I typically go to first. Just normal stuff. I will let you know what it was in the end. We found out. So the problem is that the client is basically telling the server, show me what you got. I can do a lot. And the server is like, oh, I'm sitting on a 10 gig pipe. Let's do that. Blasting packets out. So what happens if that is the case? Well, somebody's going to go into trouble mode at some point because not the full connection was 10 gig from end to end. So the funny thing in this case is if we go to, and I'm now using the find instead of the filter. Why am I using the find? Because filtering takes forever. And I just want to find a packet, not remove everything else. So the find dialog is one of the most important things if you want to do things fast in big traces, if you know what you're looking for. If you just want to jump to a specific packet, use the find, not the filter. Because the filter will run through all the packets every time when you clear it, when you set it, it's just too slow. And now you know why I'm not that happy with that find dialog anymore, because it used to be small and in a small area, so my mouse movements were really fast. Now I need to move my mouse all the time, all over the place. So let's go and say TCP.analysis. And the other thing is right now, I don't know, the find dialog used to help me with showing me what the keywords are that I can use. Now it doesn't. Need to open a bug report. Come on, where is it? There's the first duplicate ACK. So the interesting thing is, I see a duplicate ACK, a duplicate ACK, a duplicate ACK, a duplicate ACK, and a fast retransmission. Is that the retransmission for the duplicate ACK? Can you tell? Ah, good. You can't tell because FTP data is hiding what is going on with the sequence numbers. So a trick that I sometimes do, if this is annoying me, because I don't need to know that this is FTP data. I know it's FTP data. So what can you do about it? Well, simple. I go to Analysis, Enabled Protocols. I look for FTP data. I could what? Yeah, I know. I'm scrolling because Laura says don't scroll and I'm a rebel. So now the problem is then if you're enabling or disabling protocols, it needs to re-rate the trace file and it's quite big, so it takes some time. Big trace files are cool for presentations because you can stand here like, not my fault. Come on. All right, so I disabled the FTP data dissector, which means it cannot write anything onto the info column anymore. And now we can look at interesting things like the sequence numbers. And the fast retransmission is having the sequence number of something in the end 76889. The ACK was for something called 76889. Now, if you want to compare it completely, you can see what it is. Is that the retransmission for the duplicate ACK? Really? Again? Yes. Yeah, the DUPAC says I need sequence number 161876889. That's what DUPAC is saying. And this is the retransmission for that. So why are there duplicate X that keep telling me, please send this retransmission? One after, who was first? Somewhere in the front. Who said something first? The packet is stuck in the buffer. So you've seen that before. Good. Experience. Did you see it? He had experience. He had seen it before. So what happens is I'm blasting out packets like crazy, 10 gigabits, full throttle, into the next switch. At some point, the switch is going onto a 1 gigabit line, which is a factor of 10 to 1. What's going to happen? It will buffer. How big is a switch buffer? Not big enough. In our experience, and you can figure this out if you're looking at bytes in flight and stuff like this, it's usually per port 100K. So you have 100K of bytes that it can hold. But if there's a 10 gig link with an FTP server who's like, hey, I've got a window size on the other end that is 4 megabytes and throws everything at that one, the buffer is too small. No matter what you do, you can get the biggest switch from whoever, it will be too small. So what will happen? It will drop packets. If packets are drops, at the other end, you will not receive the packet, so the client will say, hey, DUPAC, I'm missing something. And the server is like, oh, he's missing something. One DUPAC, second DUPAC, third DUPAC, fast retransmission. Now the packet is sent into the switch. But what's the situation like at the switch? The buffer is completely crowded with packets that have queued already, so it's like a big funnel. And the retransmission is sitting here, and it's trying to get through, and it takes forever because there's so much stuff happening. So it takes a really long time to finally get to the client. And while that is happening, everything in the buffer is still being pumped to the client. So there's, I think I had 1,111 duplicate X, so 2,000 packets were in front of the retransmission who had to queue. It could not jump to the front of the line like, hey, I'm a retransmission, I need to get there faster. It doesn't work that way. That's something like you should try in an airport if your flight is leaving. Go to TSA and tell them, my flight is leaving, and they will allow you to do that. And retransmission can't do that. So that is the problem here. The window size is so big that the server basically throws everything at the client, and the devices in the middle get overwhelmed by the amount of packets. The first switch in the equation held some of the packets, then there was another one and another one and another one, and they were going down from 10 gig to 1 gig and finally down to 150 megabits. So there were a couple of buffers that got completely filled up. This is why it takes forever for the retransmission to arrive at the other end. And now you can tell me where this trace was taken, at the client or at the server? At the server. Why? Because you see the fast retransmission after the 3 duplicate X or 4, whatever. Yeah, we're on the server side. We're really close to where the sending is happening, which is why we see the retransmission coming out just fine, just in time, everything's great. But it arrives on the other end ages later. Yeah, we can see how long it takes to get there. If we're looking at where the packet is lost, let's say at this location, and again, let's set a time reference, and then we get down until the DUPACs are finished, somewhere here. This is the ACK that basically tells us, now I got everything, everything's fine, the retransmission arrived because there's no more help or a call for help. So how long did it take? 151 milliseconds. For a round trip time of 20 milliseconds, that is not that good. It wouldn't even be good if it's 20 milliseconds because we're basically sending, and the X coming back is just telling us, hey, continue. So this is not good. Yeah, Simon? Does that happen at the beginning of the transaction? It's somewhere in the middle because the buffer up first. The switches will all buffer stuff until this happens for the first time. Yeah, it doesn't in this case. The server is quite not having any kind of doubt about being allowed to send 4 megabytes of window size. It just keeps blasting the stuff. The speed graph is quite interesting. Let's look at the speed graph, because usually we use that speed graph to tell you that there's no problem, apparently. Yeah, slow start is something that happens too, but only at the beginning, apparently. Let's wait for the graph to paint. But you will see at the graph that there is no problem. Why? Because we're at the server side, and the server side is constantly blasting out packets, full throttle. Yeah? So it doesn't care about any lost packets, apparently. And so here it is. So it's going up, going up, going up. And I mean, the scale here is packets. I don't want packets, I want bits. I'm not sure. Maybe I got the wrong side of things. I had a different graph. Echo reply. Yeah, the problem with ICMP echo reply is not very reliable.
But you will see immediately the difference.
Yeah. Well, if you do a ping during the problem, you will see that the ping will not get answered most of the time. Yeah, because it's just crowded. Okay, let's try that again. This looks more like it. Come on, do it. All right. Well, you can see here, I had a different graph before. I don't know what I did wrong. So this is basically ramping up all the things and then going down, but staying at a steady 120 megabits per second, I think, if I calculate that one correctly. 1.2 times 10 to the power of 8, I think it's 120 megabits. Anyone agrees? I'm not sure, I'm not good at calculus. So the funny thing here is that you see, there's a huge blast, and then it keeps sending data at 120 megabits per second, which is the target speed they wanted on the other end, but it doesn't work that way, because every once in a while a packet gets lost, and then you have to send the retransmission, and you can continue on the other end, so everything gets stretched. But on the server side, it's just blasting packets like crazy. So if you're seeing the graph on the other end, which I don't have, that's the problem sometimes. You just have the capture on one end, but not the other. And then you need to think about what is happening down the line, what may be the picture on the other end. Sometimes you can only guess. But here, the server is just sending packets. And yes, it's slowed down a bit, but it kept sending like crazy. The stream graph, yeah. What's the one name of what? Wait a second, I just start the graph and then I'll try to... TCP. Stevens, TCP trace, whatever you want. Let's do Stevens. Okay, need to come closer because I'm not hearing well.
I was asking about the selective acknowledgement. If
Yeah.
it was enabled, it's TCP connected.
If it uses it, selective acknowledgements?
Yeah.
I have to check. I don't know. This was a case from a while ago, like years ago. So I'm not sure anymore. So where's the graph? 1 second. I think I got the wrong Wrong side. Can't you switch over? Switch direction. There it is. Now this looks interesting. I think I never looked at that graph before, or not in the new Wireshark at least. Looks interesting, right? Because, yeah, well, sequence numbers are all over the place. Sometimes they are so close to each other that they appear in two locations at once. So we have some packet loss here, I think. All right, so the other thing I want... where's the next do back? One second. There it is. Do back, and it says... Yeah, there's sec edges in there. All right, so I'll put the trace online, and you can work through it if you want to and find things out. In the end, it turned out that the window size was the problem, because the client set a ridiculous amount of buffer space that overloaded the switches in the middle. The reason for that was the LTE card driver of the LTE card. It had a hard-coded window size in the driver, and it overrode whatever the system said. So the LTE card was like, hey, window size something, I don't care, 4 megabytes. So the card driver was at fault, and as soon as they changed it and made it listen to what the operating system was doing, the problem went away. Yeah, so sometimes it's the driver that does that kind of thing. And I think I had more traces than those 2 or 3, but I will do a quick one in the end. This one. Let's just make the columns a bit bigger. This is an interesting case. What is strange here? There's a reset. That is okay. A reset happens. But what else? The same guy who told us, hey, shut up, is after that saying, yeah, I want to talk to you too. Like, what? Do you have any idea what could happen here? It's the problem with the medication, sort of, maybe. Actually, I don't have a definitive solution to this thing, but it's...
Would it be that the third packet never reached the server? So the third packet doesn't reach the server, the client tries to do it again, but
Yeah.
the server hasn't finished the hatching yet?
That is a possibility, yeah. So we are at the client, so we only know what the client sees. We don't know what arrived at the server. The only thing we know for sure is that the SYN arrived, right? For the SYN, we got a SYNX, so it must have been there. Everything else is unclear.
No, it isn't, because packets 789 are asking to have the third packet resent, aren't they?
It's a
From the server.
It's coming from the server, sending us the SYNX again.
After sending the reset.
After sending the reset.
Which is weird because it should flush out of the
Yeah. So yes, it is a possibility. Why would it send the reset then? Look at the timings. I mean, it's not like it couldn't have known because the packet was going one way around the world and the other thing the other way around the world. This is just mental. It's like, what? So any other ideas, Tom? Another device on the network. Well, basically, his network is like himself, a DSL router, and everything out there. And he's sure, this guy, that it wasn't the router or router. So I'm not entirely sure what's happening, but this was a case on ask.wireshark.org. But most of us said somebody's spoofing reset packets. Somebody's injecting reset packets and trying to keep you from visiting this page. And we think that the SYNX are the original packets from the server that thinks it needs to continue something, and the resets are inserted by whatever kind of device. But since we don't have a capture on the server side, we're not sure. And sometimes you can tell by a forged reset because of the TTL being different than the original server. In this case, it's identical. So if it's a forged reset, somebody doing something bad, he's quite good at hiding his location. Yeah. So these are the traces where at some point you have to say, I need more info. I need to capture this again. I need to capture, which is kind of problematic because this is a thing of the past, obviously. I can't capture the server side later. I need to redo this and capture at the server, but if the server is not mine or under my control, I'm probably not going to be able to. So sometimes it's frustrating because you don't have the other side, but you need to get as much as you can from the packet capture and deduct as much as you can, and sometimes you're just like, I think this is a forged reset, but we don't know for sure. Tom? Yeah, the TTL, I think we can take a look at it, but it's, as far as I remember, it's the same. So if you have the SYNAC here, TTL is 60, and the resets also have a time to live of 60. The IP ID here is 0, which is kind of funny. And here it's not 0, and here it's 0 again, so yes, in fact, that was one of the things where we said, well, it looks like the server is a OpenBSD, which only sets a non-zero IP ID if there's a fragment. Yeah, the OpenBSD people are very paranoid, so they always send you an IP ID of 0, unless it's really needed, and it's only really needed if there are fragments. So this looks like the resets are not from the same system, purely based on IP ID. But we don't know for sure. Yeah, so it's possible, but maybe it's not. All right, so I think I'm over time already, like I always manage somehow. So many interesting traces to look at. I still have two, but I don't think we have time to go through them. So thank you for being here. I hope you had fun. I will put the traces on my download page. Like mentioned in the agenda, it will take a couple of, don't know, days, weeks, months. Well, Christmas is quite close, so Christmas is usually the time when I have time to do something like this. So there could be Christmas presents in the form of PCAP files. Thank you.